double pipe heat exchanger for our class MENG4330. Our team consists of Omar Wendeo, Carlo Chick, Brittany Fink, Deval Patel, and Roberto Sainz. An overview of our presentation includes an introduction and background, motivation and objectives, the methodology, a discussion of our results, along with some of our references used. The main purpose of heat exchangers is to transfer heat between fluids. The main types that can be found in industry include shell and tube and double pipe. Different variables affect the effectiveness of these heat exchangers, including the temperatures of inlet fluids, the flow rates of the fluids, as well as the controllers used. These can be found in different industries ranging from petroleum to nuclear, and the goal of using these in industries is to achieve the desired temperature of an output fluid. Our project will look deeper into double pipe heat exchangers, the setup which consists of two concentric pipes. Fluids travel through both pipes, in which the one fluid usually goes through the inner tube. The flow rates can go either parallel or counter to each other. The heat transfer occurs from the inner to outer tube, given that the warmer tube fluid comes through the inner tube, and the variables that can affect the effectiveness include the length and the material of the pipes, as well as the thickness of inner tube walls. Controllers are important tools to help a fluid achieve a desired output temperature. The main use of these is to analyze the current output temperature of the fluid and adjust the inputs in order to achieve this desired temperature. These can be done by adjusting either one or more inputs of the system. There are different types of controls to consider depending on the industry and task. These range from the PID, the feed forward, and also the cascade. For our project, we will look at each one of these and compare the effectiveness of these controllers in a double pipe heat exchanger.
Motivation and objective. Project objective: to develop a control system for heat exchangers so that the desired outlet temperature can be achieved by controlling the flow rate. Motivation: an understanding and prospect of improving the design, modeling, and control of double pipe heat exchanger in MATLAB Simulink at different conditions. Now we have methodology, where we have a model of a double pipe heat exchanger was created using SolidWorks. Mass and energy management methods are used to create the mathematical models. MATLAB and Simulink will be the tools to simulate the heat exchanger and its controller, and we will also show the tuning on the feedback controller. The main objective is to test the effectiveness of the feedback and the feed forward controllers to control output temperatures, fluid, and compare the effectiveness of each.
Here we have our assumptions: negligible potential and kinetic energy, no phase change of the fluid, flow along streamline, standard ATM, parallel flow, fully developed flow, constant fluid properties, clean heat exchanger with no fouling, steady state flow, incompressible fluid, well mixed tanks and heat exchanger, no external work, hot fluid flows on the inner pipe, cold fluid flows in the annulus section, heater and chiller effects are instantaneous.
Here we have a model created in SolidWorks. The model on the left is a double pipe heat exchanger, which is a control volume. The model on the right shows the overall system of the double pipe heat exchanger. The arrows show the parallel flow. In red is where the hot fluid flows, and the objects in blue show where the cooling fluid flows. The two objects in the back are our boilers with an integrated control system. Next, we will have results and discussion.
Here we have our givens. We have separated them out from the hot side at the top and the cold side down at the bottom, and we can begin our problem. Our properties from the tables. As you can see, we separated from the pipe side again, hot side, and then the annulus, the cold side. We also have our water and the different rates that they are at, different specific heat values. This will help us formulate the next steps of the problem. Here we see our mass balance equation, and we can see that no accumulation of the mass in the control volume. It is a steady state mass flow. We can see that the flow in is equal to the flow out.
Now we begin the energy balance. On the top you can see the general energy balance equation. From our assumptions, the kinetic and potential energy are negligible and there's no work being performed on the system. So our energy balance equation drops down to the change in energy equals to energy in minus energy out plus heat added to the system. After substituting our equations for E, M dot, and Q dot, we get the equation on the bottom. With our general energy balance known, we can now calculate for the pipe and the annulus side. On the pipe side, you can see that we are subtracting the Q dot value. This is because heat transfers from the hot to cold side, whereas on the annulus side, we are gaining the Q dot, as well as on the annulus side, we are gaining heat provided from the surrounding. Substituting the Q dot equation, we get the following pipe and annulus equations for energy balance. Begin to analyze the system by calculating the heat from the surrounding. To do this, we need the convective heat transfer coefficient. We know the thermal conductivity of PVC as well as the diameter, but we need to calculate the Nusselt's number. The following equation is used to calculate the Nusselt's number of an air over a cylinder. We have the Reynolds number from a table, but we did need to calculate the Reynolds number. Given the parameters of the atmosphere, we calculated our Reynolds number, and from that we were able to get our Nusselt's number to finally obtain our convective heat transfer coefficient. With our convective heat transfer coefficient known, we can now solve for A, the surface area of the heat exchanger, and the difference in temperature, which is the average annulus temperature minus the surrounding temperature. With these values, we get a heat added from the heat from the surrounding of negative 73.004 watts. Now that all variables are known, we can analyze the system at steady state conditions, meaning the left side of the equation is at 0, to solve for our overall heat transfer coefficient, U of A. On the pipe side, we got 4.608 watts per Kelvin, and on the annulus side, we got 4.851 watts per Kelvin. The difference is primarily due to the added effect of the atmosphere on the annulus side.
So here we have our feed-forward controller block diagram with a delay in time with a linearized S function. So here we have our controller responses from our feed-forward controller, and we added a delay time of 2 seconds, and as you can see, these are the following two responses that we have gotten. Now same approach, but now we have included a PID and get the following results.
So here we have the feedback controller that we used for the double heat exchanger. We also added a delay to the inlet of the temperature hot, and also another delay to the temperature cold. That are shown here. See through the highlight. This is a delay we added, and this is another delay. And then we added a delay of 2 seconds each at each one. Here we have a feedback controller with a delay PID. And here with the delay, as we mentioned, of 2. Now here we have the same feedback controller delay with PID, but here we applied a tuning with a overshoot of 5% and a rise time of 5.24 seconds, which refine our values compared to the PID without a tuning in slide 23. And also, as compared to all of other graphs, with the PID tuning came out to give us the best result possible, as there is a less overshoot, as you see in figure 2. Here we have the figures 1 and 2 showing for a feedback control delay with a PI tuning, and the tuning we use here was with an overshoot of 10% and a rise of 3 seconds.
And here are the controller responses for our feed-forward feedback controller, PI. And as you can see, we have some oscillation occurring. Same thing over here. We have for the PID method, we have oscillation in the plots, and we can minimize this by using the transfer function tuning method.
Here we have our references.